Hello and welcome to this sixth tutorial of the course uh, Reinforcement Learning offered by NPTEL. I'm Mohit Pot, the TA of this session. So in the last week, we have, in the lecture, uh, following things are covered that I have seen. Monte Carlo method, then TD learning, and then Q learning. So these three things are three different things. With first two things have same objective. Q learning is slightly separate thing. So what these things are and what are the differences, what are the similarities, and every details, every conceptual details behind these things will be discussed this in this tutorial. So first, let us recap our journey so far. We have seen bandit algorithms, but that we are not going to discuss. Let's start from MDP. So MDP, what did we study? The model and what is MDP, and then we first studied specifically something called planning. What is planning? Given the model, or model is another name for the MDP itself. Given the model, that is the MDP, finding two things: optimal value and a policy that attains the optimal value, which we call optimal policy. So I have told you that there is another component, which is learning. And for MDT, we want to employ a good policy which will control the process and give us good cumulative reward. So it's not only learning, but learning and control. So the control part I am keeping in the bracket because uh, we are not directly jumping in there. So another component is, and one is planning, another is learning. But learning of what? So general objective of our course or RL is learn the optimal policy, learn the best policy, and best means optimal policy with minimum resources, or utilizing minimum resources. By resources, we mean that less number of samples, less number of trajectories. So by resources, we mean samples. So in part of this tutorial, we'll look at specifically to a subproblem. and which is called policy evaluation. So why do we do policy evaluation? Because that could be useful in order to solve the main objective. That is what we are calling here general objective, that to learn the optimal policy. Unless you learn, uh, unless you know how to evaluate a policy, then how can you compare two policies and find the better one and eventually the best one? So that's why policy evaluation is an important problem. So in the last tutorial, I remember that we have discussed two methods of evaluating a policy. But before that, let me recap what we mean by evaluating a policy. Given a policy by we we are interested to find V pi s. This is the state, initial state, and this is defined as expectation over policy pi, sum of rewards from t equals to 0 to infinity, gamma is to t, r of s t a t, given initial state is s. And this expectation over pi means the action AT is taken according to policy pi. So this thing we want to evaluate. And if we know the NDP, which is a 5 tuple, if you remember, state space, action space, probability kernel, transition probability kernel, reward function, and discount factor gamma. Then we have two methods of evaluating a policy we have discussed. First one is through Bellman equation, and basically writing the Bellman equation in matrix vector form and solving a inverse problem in matrix inversion problem. V pi equals to R pi plus gamma times P pi to V pi. I think you're understanding what I mean by V pi, R pi, P pi, and yeah, these three things. So if you solve this, then basically V pi will be equals to I minus gamma P pi, where I is identity matrix P pi inverse R pi. Given that you know the model, you know P pi and R pi, and hence you know V pi. And the second method we discussed, that is iterative method, that you start with V0 and I equals to 0, while true for increment I, and for every s, for s in state spaces, you update vi, and this is equals to r is by s. Here I'm assuming that this pi is deterministic policy, but that is not necessarily easily changing to randomized policies. and then a stopping condition that says that if vi minus vi minus 1, the infinity norm uh, goes below some parameter epsilon, then you break this while loop. Well, so these were the two methods of evaluating policy, given that you know the model. But what if you don't know the model and there comes the learning component of our course, and which is basically the main focus. Learning, which basically answers the following question: what if we do not?
Avik, one question here
Yeah, sure.
is in the second part, we do the convergence of VI, like the Banach space contraction thing, right? In the
Yes.
second part. So, irrespective of phi, my question is, would you always get to the V star or the
No, no.
uh,
So here I am fixing the policy. You are not looking. So in that iteration, value iteration, if you're talking about, there you take a max, right? Max overall actions. So
yeah. So
that
what I
iteration,
wanted to ask is, given any policy, you let's say converge to a VI, then you do the max of that, you will come up with the optimal policy, is it?
yes.
So let's say you start with an arbitrary policy where you can
No, no.
go. Hmm.
So when you are doing value iteration, I'm talking about the other algorithm where you don't have any notion of policy at all. So in every step, you are basically looking at the maximizer action and updating the value iterates accordingly. So that is your value iteration. That is a different algorithm than this. This is policy evaluation. Here you are
No,
not taking any max.
I understand that part. You're just saying that it is a policy evaluation. What I'm asking is, if given any policy, will this converge to let's say some V, and then if we do the max part of it, uh, will that give us optimal policy, or that is these are two completely different things?
Okay, so what I have understood from your question that you are asking, say you have every policy possible, and then you are evaluating the policies. So you have a set of numbers and corresponding policies, and you are looking which policy is maximizing the values, and you're looking at the maximum value and corresponding policy. You are asking whether this maximum value will be the optimal value and whether the corresponding policy will be the optimal policy. Is it your
Yes,
question?
yes, yes, yes.
Yeah. Yes, that will happen.
Okay, so irrespective of what policy you will start with, if you apply this like iterative procedure, converge to a V star, converge to a V which will be V star, and then find out the argmax, it will be optimal policy, right?
Yes.
Okay. Good. Okay.
So yeah. So when we you're talking about learning. So learning is basically answering this question that what if we do not know the uh, MDP? Uh, Not knowing the MDP means you do not know the reward function and the transition part. So one method could be this. I think is not, was not discussed in the lectures, but I thought of discussing in very brief. That is, so learning means we are looking at only policy evaluation. So if you are given a policy, you are trying to find out V pi. So one method could be that play pi for n time steps Then estimate R pi and P pi with R pi in hat. I'm just naming this P pi uh, in hat. So what are these things? R pi in hat is basically the number of times t equals to 1 to 0 to capital N minus 1. You have played, if you have encountered action, so there it should be. You have encountered action, uh, sorry, state S and divided by the total number of encounter of action, sorry, state S equals to 0 to 1 minus 1. Indicator function is equals to S. So if you have encountered state S enough number of times, then this quantity R hat pi n S is a good estimate of R of S pi S. And what about this P pi? So this is not a function of state, rather it's a function of state cross state. So from so what will be this quantity? So if you think carefully, please. Yes, sir. Someone said something.
Yeah, this will just be the ratio of number of times we have gotten into different
Yes.
states from this state.
Yes. So this is basically how many number of times you have been in state S, and that is the denominator, and the numerator is out of those times, how many times you landed up in state S prime in the next state. That makes sense, right? So in that says St equals to S and St plus 1 is S prime, and the entire thing is divided by number of times you visited state S. Now it may occur that the denominator is 0 because you have never visited state S. In that case, you take minimum of this and 1. So this is estimate of P is pi is prime. So this you can see that P hat pi n is a proper probability distribution over next bit. So given you have this estimate, you can now compute P pi hat as I minus gamma p hat by n inverse r by n hat. So you just replace your p and r with these things. So this is a method that makes totally sense, and people have worked on how much error there will be given you have n samples. Well, so next thing is, what if we do not try to estimate the model? Okay, before going there, researchers have named this type of method something specific. So they call it model-based method. Model-based methods. Ultimately, we are estimating the value function, but through estimating the models. And next set of uh, this is a bit complicated because you are going through a route, but uh, people have uh, analyzed both of this type of algorithms. And the next is I'm saying both of them. So one is this, and another is where you directly try to estimate the value, which is called model free methods. And one of the method here is Monte Carlo. So these are policy evaluation algorithms, but for proper reinforcement learning algorithm, where the objective is to what I was discussing in the beginning, uh, that is to learn the best policy utilizing minimum resources. There also you will see this two division of how we use the samples, model based or model free. Well, so now let us discuss this Monte Carlo method. What is Monte Carlo method? That says that you run a trajectory, then you will get a sample value function. That is, if you run a trajectory, you get a sample function. What does that mean? If you run a trajectory, you will get R1, so starting from R0, so R0, R1, R2, and so on. So this is an infinite horizon problem, right? So given you have incurred all this, so V, what do we, let's write V hat. And here say your state is S0. So V hat S0 will be sum over equals to 1 to infinity. Gamma raised to T, sorry, equals to 0 to infinity, gamma raised to T, R T. So that is your one sample, what you have incurred in one trajectory. We'll discuss this in detail, but first, let us see one important issue. Here, this trajectory is infinite length, right? So it's not practical in real systems. You can never have infinite length trajectory, right? That will take infinite time to be generated. So you have to truncate the trajectory somewhere. So what will be that? Say, you are allowed to make epsilon error. So what that basically means is we had, okay, I have not written pi here, but there is a pi. Let's not write pi because everywhere there will be a pi, so the policy is fixed. V hat minus V. If that is less than epsilon, we'll accept it. So if you are allowed to make this much of error, then if you look at this summation, first one is R0, second one is lambda times R1, third one is lambda square R2, and so on. Look at mth step. Okay, this is m. So it will be gamma raised to n minus 1 R n minus 1 and then gamma raised to n and so on. So my question to you is, what is this upper bound of this summation, given your reward is bounded in 0 to 1? So it's easy to see that the tail sum of rewards from n plus first state is bounded by gamma raised to n by 1 minus 10. If this amount, if this is less than epsilon, then you are okay, right? Then if you estimate the rest uh, accurately, then you will be inside epsilon margin of error. If then the error would be acceptable. So then it turns out that n has to be greater than log base gamma, or will it be 1 minus gamma? Sure.
Abhik, that m
Yes.
plus one step should be 1 over 1 minus gamma raised to m, no?
Sorry, I couldn't understand.
The m plus first step is bounded by, you have written gamma raised to m over 1 minus gamma, right? So if that is the geometric series, it should be 1 over 1 minus gamma raised to m, no?
No, so
1
what
over
is the
1 minus
next
gamma.
term?
Okay.
Is it, you understood this?
Okay. Got it. Okay. Makes sense. Sorry. Thank you.
Yeah, I think this will be okay. Let me calculate without any 1 by 1 minus gamma epsilon is 1 by gamma raised to n. Well, so if gamma n is greater than this, then we are fine. We are within limit of the error margin. So this thing we'll keep in mind, and we'll just sample m length trajectories. So let us draw two trajectories. So these are states. Let us consider there are 4 states, 1, 2, 3, 4. And starting from time equals to 0, 1, 2, 4, so on, till time n. So let we have two trajectories. Was also draw some vertical lines. So let us consider two trajectories. First one is in time 0, it's in state 2. At time 1, it's in state 4. At time 2, again, it's in state 2. Time 3, it's in state 3. Time 4, it's in state 4. And uh, time n, it's in state 3 again. So just to so that we can distinguish these two trajectories, I'll draw another drawing this times. And there is another trajectory, which is trajectory 2, so, which also starts from state 2, then goes to state 1, then again says state 2, then state 4, then state 3, and at state n, time n, it goes to state 2. And so this joining line doesn't have any meaning, just because the process is defined only on discrete time. This is just to so that you can differentiate these two trajectories. So there are two methods you were, I think, introduced to. First one is first visit method. So like that, say you have n number of trajectories. first visit method. So there you have the hat, and I'm considering this violet one to be trajectory one, green one, trajectory two. So the superscript I will be writing V hat one. That superscript will denote the which trajectory it is, and then state. So we had one at state two. So first visit means we'll look at the first time the process has visited state two. So that time is equals to 0, right? So we had one. Okay, and another thing, we have to write which reward we are incurring at which state. So let us write that. Right. R L T be the reward incurred at th time in lth trajectory. Can anyone of you tell me now what is the estimate this V hat 1, 2 will be according to this notation? So it's about first trajectory always. So it will be R1. And it will start at time 0 because at time 0, the state 2 is visited. Right. So it will be 0. And then since this is gamma discounted, for the next step, it will be multiplied, the reward will be multiplied by gamma. Gamma times R1, 1 plus gamma squared times R1, 2 plus so on plus gamma raised to n times Rn. That's what it is. And someone now please tell me what will be this V1, 1. Look at the trajectory and tell me.
It will be R11 plus gamma R2.
Yes, exactly. R1, 1. There's R1, 2. And similarly, okay, so next you see that the process has visited state 2 again. But that will not count because from state 2, we have already had an estimate which has started at time t equals to 0 itself. So that will not take care of. Then we had 1 of 4. That is R3, R1, 3 plus gamma times R1, 4 plus gamma times R1, 5, yes, so on. And then we have 1, 3. That starts from R1, 4. That's now times R 5, that's 6, that's so on. So this is what it is, and the rule is basically collect at most one sample of for each state, and starting from the first visit to the state. Now, after collecting all this V1, V2, sorry, we had 1, we had 2, we had 3. Then after collecting these trajectories and estimating the value from each trajectory, we have to average. So now we take average over trajectories. We had 5 cases. Now, say we have collected n trajectories, then equals to 1 to n. We had L case times indicator. So V hat LS will make sense only then when the state S is visited at least once in this trajectory. So the indicator S is visited in trajectory L. And this by the total number of times trajectory L is visited. 1 and okay, so that fully makes sense. And then there is another method which is called every visit method. What does that mean? So here, every visit so here we have visited this state twice. In both the trajectories, we have done that, right? But first visit says when you were visiting the state for the first time, you compute this estimate from that time onwards, and that's it. You have to, you don't have to compute the estimate again when you are visiting it second or third time. So every visit method says that no. So from here, from time 0, you have one estimate that is for state two, that is we had one where we didn't name it anything, but this is say subscript 1 because uh, this is when the state 2 is visited for the first time. But here the every visit method is saying that from here also you compute another estimate, and that will be we had 1 2 of 2. This subscript 2 signifies that this is for the second visit to the state 2. And if in the somewhere in between this state 2 is visited a small mth time, then from there also we'll have another estimate that will be we had in superscript 1 of 2. So instead of one estimate from one trajectory, we are having as many estimate possible from one trajectory. If a state is visited m times, then we'll take m trajectories. So that's the method. There is nothing complicated in it. Well, so now we'll discuss this Monte Carlo method. Okay, let me write this every visit method estimate. We had 5 days. It's 1 to n. Now, in every trajectory that state is visited certain number of times. Let us write that number by m l is. So I equals to 1 to ml is b at l I s divided by sum of l equals n. L. So here we do not need to write this indicator function because ml is that variable is taking care of that. Okay, so that was every visit method. Now, this I have not discussed in any of the previous classes, but are you introduced to stochastic shortest path problem?
I have not watched this week's lecture yet, but until last week it was not discussed.
Okay, so let me take some time to introduce stochastic shortest path MDPs. So where this is basically where the horizon length is finite but is random. So with probability 1, it will be something finite. It will not go to infinity. But also it's true that it will never be deterministic. You cannot write some capital H to denote that horizon length as something non-random variable. So this, if you think this H horizon is random variable, then what you get is stochastic shortest path problem. And also it's useful to uh, discuss it in cost setup instead of reward setup. So we'll consider that R is negative. Say R will be in -1 to 0. However, let me take some time to from where I should start. Wait, stochastic shortest. So this is basically MD is A, P, and R, such that R is function from state and action to -1 to 0. Since we are talking about reward setup, so I don't want to change. So I just made reward negative. And there is a termination state. It is says bar, small s, such that R of S bar A is equals to 0 for all actions. What does that mean? So you see, if you have reached this bar, from there onwards, you will get highest reward possible, right? Do you agree with me? 0 is the highest reward, right? Because the reward function is between -1 to 0. So if you once hit this termination state, S bar, from there onwards, you are getting highest reward. From basically you want to hit this state. So if you are say you are modeling chess, playing chess, S bar is you can think uh, as a state which where you win the game. Okay. So the termination state is your goal state. You can think in that way. Okay. So and say you are guaranteed say under policy 5, you were guaranteed to reach this bar with probability 1. And say where you hit the this state is bar, is age, which is the random variable of the horizon. Actually, if you think carefully, that it says that if you hit the termination state S bar, your process terminates then and there, because after that there is no point of making uh, choice of actions, because every action is same from there on. This is the like a mathematical way of uh, formulating a finite horizon problem in infinite horizon setup. Okay, so now what we'll do is we'll discuss this Monte Carlo method in this for this setup in particular, and we'll see some variations, and uh, we'll see if we change. You are also introduced to 3D learning, right? We'll see that if we change some parameter, then Monte Carlo method and 3D learning are related. So if you change the parameter value to 0, it will be 3D learning. If you change the parameter value to 1, it will be Monte Carlo. If you keep in between, then it will be something in between. So that will be an interesting exercise, and that will complete the rest of the today's tutorial will be consumed in that. Right. So Monte Carlo. Okay, there are n states. Okay, so before going there, let us assume this. State space is this set is 0, is 1, and is 5. So in normal state, capital N number of normal states and one termination state. So on the image visit to state S0 set, let R bar is 0, comma n. Or let me just write is I. I don't want to be specific to one state. Is I, which is not termination state. Say n, which is okay, there is a problem, that is I also denotes the state at time I, right? So I need to use something else. Okay, let's just keep it S, which is not termination state. State S not equals to S bar, state M. And this visit happens, say, at time T S comma N. Let R bar S comma N, that denotes T equals to S comma n. Say the process ends at time t. So process ends means the process hits the state is bar at time t, and this is a random variable, not something deterministic. R t. Then this is the return the of state is for mth time visit to state is. And we are playing a policy pi. Hence, what is the and say this is from trajectory. So we are say talking about one trajectory. So we had this. What will that be? Will be one by say we are visiting uh, this state is capital MS times. Then it will be average of all these cumulative rewards, right? I equals to n equals to 1 to capital N S R bar is formula. This is estimate of the pi is. Pi is the policy we are playing. Right. So there is a iterative way of computing this. So this where we had this is something we are computing at the end of the trajectory. We are just collecting this R. We are computing R bar S comma M every. I mean, we are keep on computing this thing R bar S comma M, and then at the end we are averaging all of them and finding this estimate. What if we want to calculate this iteratively? So iterative computation of the act. How do we do that? So we had this, we update it by, so this is, we cannot write it in mathematics. So we have to write it in the coding language. We had is, we update that with we had is plus some lambda time, lambda m r bar I m I s comma m minus j minus b hat is where, or you can just write it as m. So this is b of m and this is b m minus 1. So also b where okay, writing yeah, lambda, where lambda m equals to 1 by n, with p at 0, s equals to 0. So you'll see that this will result in, if we compute this, then this at the end we had in s will equals to p at s. Okay. Now we can write this iteration r bar m is comma m minus p hat m minus 1 is, that we can write in a little bit different way. P hat m to r bar sn, that we can write in this format. What it was r bar is comma n, that was this sum, right? So we can write, we can replace this r bar sn with this sum. So that will be r t sn plus r t sn plus 1 plus, okay, so there is and so on till r capital T minus b at m minus 1 is. So now we manipulate this term, uh, the last term, with some plus and minus other terms. We'll take the first term of this reward, s comma n. We'll add b m minus 1 at s t s comma n plus 1 minus. So remember that s here can be replaced by. So when we are updating this v hat in, that means we have visited s at time visited s at time t s comma n, right? That's what the definition is. And hence we can replace s by s subscript t comma subscript s comma n. Hope this is clear. S t comma s comma n. So that is always equal to s, right? Hence s comma, sorry, it's a subscript t subscript s comma n equals to s. So that's what we did here. So we have not written this many terms and added something extra. This one. This we have added. This not written. So what we'll do in the next step, we'll take one term from here, so the first term in the not written terms, R T S N plus 1 Then we'll add something else and subtract the term we have written in the last step. We have n minus 1 is t s comma n plus 1. So what we'll add is not difficult to guess. That is b hat n minus 1 s t s n plus 2. The next step. So let us erase all this. And then we keep on writing. Last step is RT plus B hat n minus 1 is T is cap is capital T plus 1 minus B hat n minus 1 is capital T. So you ask me that this term is not cancelled, right? Not cancelled. So this term cancels this one, this next term, next second term, and this one is also this one will be cancelled with the previous term here, which I have not written. This will be cancelled with this one, and so on, right? But this term will remain. This term will remain because the same term was here, same term. So we are not worried about this one. We are not worried about that term. But what is not cancelled is this one. This term. But look carefully. That is at s t plus 1, you know your process is at s bar, and whatever action you take, it will give you reward 0, and it will not move from that particular state. Basically, the process has terminated there. So if you know that whatever actions you take from a certain point of time, you will get only 0 reward. What will be the value of that state? That will be 0, right? So we do not need its estimate. This estimate will always be 0. And st bar, st plus 1, that is nothing but s bar. So if you know the true value, why will go for the estimate? That's the point. And this is equals to 0. Well, so this term, this RT plus V hat n minus 1 is E plus 1 minus B of n minus 1. So I have missed n minus 1 here. B at n minus 1 is T. This is called, first of all, this we name as E T. T, and this is called temporal difference. Temporal difference is the full name of TD. So you have encountered the term TD learning. So this is what that name comes from. Why it is called temporal difference? So based on the samples you had till TM, TSN, you had this estimate of the value function, the second term, which is you are subtracting. And based on the additional sample you have got one reward. Additional sample means you have got one reward, which is this, and you have got the next state. So if you go with the value, if you go with this Bellman equation, what does the Bellman equation says? It says that ds t equals to expected value of r t plus d of st plus 1, right? If you think carefully, that's what Bellman equation is. And what it's saying that this term is nothing but an updated value function, given that you have one more reward and one more state, and you have not taken the expectation. Expectation you could not take because you have finite samples, and that is in particular one sample. Expectation is not possible to take. So if you remove the expectation, this is exactly your value function estimate. It can be used as value function estimate. So by gathering one sample, whatever difference you have in value function, that is basically your new estimate minus your previous estimate. That is the improvement towards a better estimate you can think of. So that's why you add this temporal difference terms with your previous estimate. That is this one. You are adding your temporal differences with the previous term. That's the idea of temporal difference learning. And what you have seen is, given you have this many samples and all, your Monte Carlo method that can also be written as temporal difference learning. But here the difference is you have so many terms. You have so many terms. So it's I say T minus TSN TD terms. Right? What we can do is this you can only write when you have all the entire trajectory ready. Instead, what we can do is what TD learning does is you take the only first TD learning. You take only the first temporal difference term, that is Vn minus 1. Sorry, Vn at s equals to Vn minus 1 s plus gamma n times r t n s plus p m minus 1 and s minus, sorry, s plus, s plus I mean the next state t s comma n plus n, right, minus p n minus 1 at s p comma. This is what TD learning is. Okay, so this is what Monte Carlo and 3D learning are. But can we write in a generalized version that can we introduce some parameter so that for some parameter, extreme value of the parameter, the algorithm will be 3D learning, and some other extreme parameter value of the parameter, the algorithm will be Monte Carlo method. So that's what is called TD lambda. We call this TD lambda algorithm. So we recall Bellman equation. V pi is let us write as t because there will be some sense of time there. T pi r t plus t pi is t plus 1. So this is called, we can call it one step Bellman equation. But you will understand it shortly. So V pi is t, write this same equation with a slight change. Now V pi is t plus 1, that we can write as expectation t pi RT plus t plus 1 plus V pi st plus 2, right? And there is no point of writing these two expectations separately, so we can write it once. One plus V pi st plus 1. And similarly, we can keep on expanding this thing. At the end, we can write this as RT plus 1 plus the RT plus L plus E pi is 3 plus L. Now, if we take the weighted sum of this, so what if we do the following? So here, if you see that uh, sum of this weights, so we have weighted this with, so here the image term we have weighted with this. This is the weight. We have weighted each term, and the sum of these weights equals to 0. That sums to 1. So hence, the left hand side will be V by S T, and the right hand side there will be something else. Instead of writing each Bellman equation, you have written the weighted sum, and the weight sum of the weights sum to the sum of the weights is equals to 1. So hence this summation we can write as 1 minus lambda. At first, there are terms which are rewards, right? So we can write the rewards terms as follows. Summation. So there are two summations, L equals to 0 to infinity and summation M equals to T to L. Sorry, I should do something else. This should be M should run from 0. And here instead of M, I should write T plus M. T plus M. Okay. R of T plus M. Lambda is to and plus we can write this term. We can take 1 minus lambda inside and L equals to 0 to infinity. Lambda raised to L minus lambda raised to L minus L plus 1 times J pi, sorry, E pi is T plus L. Okay, so here also it should be T plus L minus T. Okay, so if we simplify this thing, the first term will reduce to this expectation of summation n equals to 0 to infinity lambda raised to n r t plus n, and the second term will reduce to expectation n equals to 0 to infinity lambda raised to n j pi t plus n minus j pi is
V pi.
t plus n plus 1 plus, oh yeah, v pi, sorry. T plus n. Okay, now if you take hopefully I have written correctly. Yeah, hopefully it's correct. And then if you see this, if you combine these two expectation, n equals to 0 to infinity, lambda is to n, r t plus n plus t pi is t plus 1, t plus n plus 1, t pi is t plus n. So this is what the generalized expression is. Now, if you have this lambda equals to 0, if lambda equals to 0, okay, so what I think is there will be a additional term of d pi st. So from here to here, this term will come. So for lambda equals to 0, d pi t. So we are not worrying about this d pi st at all. But for lambda equals to 0, this equation we are trying to estimate, improve the estimate, right? So we had m st. We are trying to improve it by we had m minus 1 st plus expectation is possible to take m equals to 0 to infinity, lambda raised to m r t plus m plus t pi x t plus n plus 1. So in this equation, now if you take lambda equals to 0, you'll get TD0, or which is famously called as TD learning update. And if lambda equals to 1, then you'll get Monte Carlo. So all the terms here will be, so that exactly matches with the previous expression we have written, Monte Carlo. Okay, so that was the connection. And next topic is covered in the last week lecture is Q-learning. So I'm not going to discuss Q-learning today. But next day, what we'll do, we'll code these algorithms in Python, including Q-learning and some other algorithms which we are expecting to be covered in the next week or week 7. So these things will. So next lecture and tutorial, I'm planning to be do entirely on or entirely with Python coding. So yeah, that's it. Q-learning and why it is needed, that will also covered in the next video. Now, if you have any question, please go ahead and ask. Okay, so no one has question, is it? Okay, so we are stopping today's tutorial here, and we see you in the next tutorial. Thank you.